Transformers represent an important and expensive link within the electrical power generation and distribution network. A failure can cause network outages and, related to it, immense costs. The deregulation of the energy market has led to a lot of pressure on costs, and this development forces transformer operators to change maintenance from a regular time-based to less costly condition-based approach. With the advancing age of transformers, regular checking of the operating conditions becomes more and more important. Dielectric response methods allow the direct analysis of the solid insulation of the transformer. They can also be utilized for the evaluation of bushings and the insulation properties of motors, generators, and paper-insulated oil-filled cables. But first, we should consider what leads to the degradation of a power transformer. One cause is moisture entering the insulation. This can be due to a number of factors, such as the transformer's breathing, which may bring the oil into contact with the atmosphere. Leaky seals, transformer installation, or repair can also lead to an enhanced moisture level in the insulation. The normal aging process may also lead to the creation of water as a byproduct of the breakdown of cellulose. From Segrè findings, the moisture content can increase by 0.1 to 0.2% per year due to cellulose aging, even if the transformer is completely sealed. Water in the oil paper insulation causes three dangerous effects: decreased dielectric withstand strength, acceleration of the aging process of the cellulose, and the emission of gas bubbles at high temperatures. Based on these facts, moisture evaluation is vital to prolong the lifespan of a transformer, to determine if drying is required, and also to ascertain if the drying process has been successful. The traditional method of assessing the amount of moisture in a transformer required the following steps: drawing an oil sample, taking the sample to a laboratory to evaluate the moisture level with the aid of the Karl Fischer titration method, then translating the resulting amount of moisture in the oil to moisture in paper by using equilibrium curves. This method of moisture evaluation is only an approximation, and it leads to further questions. How does the transportation of the sample to the laboratory influence the final result? Is the titration method also valid for an aged transformer? What influence do dynamic temperature and load changes have on equilibrium? Are the equilibrium curves valid for all types of oil? And are the curves accurate enough to give a realistic result? These uncertainties, plus the roundabout way of approximating the moisture in paper via the moisture in oil, call for a more direct and precise method. Dielectric measurement offers a useful tool, especially for the evaluation of the moisture content, as both conductivity and polarization of dielectrics are values influenced by moisture. During the dielectric measurement, the insulation is exposed to a wide band of frequencies, and its response to these is recorded. These results give a clear picture of the state of the transformer. Displaying the dissipation factor over a wide frequency range uncovers the specific properties of the oil, the insulation geometry, and the solid insulation. Moisture in the solid insulation becomes especially visible at very low frequencies. This method not only measures the actual moisture content in the solid insulation in a direct way, it is uniquely non-invasive and temperature-independent. Plus, the interpretation scheme for frequency domain measurements is scientifically approved and internationally agreed on. With the Dirana, Omicron Electronics offers a reliable and fast dielectric response analysis comprising all these benefits and more. Compared to other dielectric methods, around 75% of the measurement time is saved by combining frequency domain spectroscopy at high frequencies with time domain measurement at low frequencies. Additional time can be saved by measuring simultaneously with both input channels and by using the forecast algorithm. The Dirana's moisture determination is based on a comparison of the transformer's actual dielectric response to modeled values based on data acquired in laboratory tests. An algorithm rearranges the modeled response to match the actual results and delivers the values of moisture content along with the oil conductivity. The software automatically compensates for the influence of conductive aging byproducts in the insulation, which would otherwise lead to an overestimation of the moisture concentration. It also features built-in expert knowledge and an intuitive user interface, and predefined tests for all transformer types, plus the software's step-by-step guide through the measurement make the operation easy. Only the insulation temperature has to be entered by the user. Additionally, the Dirana's software immediately classifies the results of the measurement according to the IEC 6422 standard and shows the user whether the transformer is dry or wet and if further actions are required. The software utilizes an easily understandable color code for its assessment. The diagnosis of moisture is a very important condition-based technique. Dirana is a comprehensive but easy-to-use and dependable tool for condition-based maintenance. The measurement over a wide frequency range provides a degree of accuracy which was never previously possible. The fast measurement procedure is based on a combination of frequency domain spectroscopy and time domain measurement. Built-in expert knowledge and 2 measurement channels reduce the measurement test time, and the measurement can be performed directly after the transformer has been shut down, as equilibrium is not required to achieve a correct result. As well as for power transformers, the Dirana can be used for other high-voltage assets, including bushings, cables, generators, and motors. The Dirana provides the data that lets you feel confident about your transformer's insulation condition.